this is water in terms of pH, relative average pH, where you're at. And pH of sediment, most sediment is right in this zone. Okay? So then when you look here, what was your specific question?
Oh, I was just wondering which range of aluminum was most affected in terms of pH.
5.5 to 8.4. Above 8.4, you start to see the aluminum phosphate starts to solubilize. Okay? Below 5.5, you start to see it.
What's the form of aluminum that you're talking about?
Well,
We're talking about physics. What is it is?
There's several different forms you can apply, but we'll get to that. I'm a geek, so you got to have a little chemistry. Okay, so lanthanum is slightly up here. We're not sure of the upper pH, whether it's 8.2, 8.4, that it holds, but we do know below 7, it starts to not hold phosphorus as well. This is why it's good medicine. Okay, put it in your stomach, it's acidic reaction, the lanthanum dissolves, and then when it goes to the duodenum, the pH goes to 7.2, 7.4. The lanthanum grabs that phosphorus and doesn't let it get to the kidneys. It flushes out of your system. That's why it's good for kidneys. Okay. So, similar ranges. As I said, calcium, once you get below 8.4, starts to lose its affinity for phosphorus. And then iron is redox in pH. So once you get acidic conditions, iron is going to start to go. Okay. Aluminum sulfate is the most common, answer to your question, is the most common compound added to alum, and I'm going to go through several slides talking about that. I'll also bring in the other metals there. It's cheap in North America because we have adequate supplies for mining. Some of it's coming from China now, but it's still cheap and available. Aluminum, there's different compounds of aluminum, such as aluminum chloride, other things that you can use. It's just what's cost available, both in terms of transportation, the cost of getting it there, where it's locally produced, and the cost of the process to produce it. In most cases, in Manitoba and stuff where we've planted this, and continental U.S., alum is the cheapest form that you can get. Okay. Other places, it varies. Okay. We've already talked about that, so it's just turns to be the most cost effective, so that's what I use. Also, to your question, when you add aluminum into water, its affinity for phosphorus is huge. So it grabs it and it doesn't want to release it really until it gets really low. But you will over time. This is an instantaneous pure system. You get into a heterogeneous system, that's why I use 500.
Eric, you go back. Why does it bend down a little bit at the bottom?
Here?
Yeah.
Well, I don't know. Not my graph, I stole it. I think it's just the
What's on the-
observations I had. I don't know.
What's on the other axis?
The speciation.
Percent species.
Percent. Okay, again, it's just cheap. It's easy to handle. It binds on lots of conditions, so it has the advantage. That's why it's supposed to. It's used a lot. There's been 180 peer-reviewed journal, long-term studies happening all in different journals. So we're across Europe and the US. So we know a lot about it. But here's your basic reaction. With alum, aluminum sulfide, it's going to react and it's going to form aluminum phosphate. But in reality, in the real world, what happens is aluminum hydrolyzes, forming aluminum hydroxide, which is a polymer that's insoluble, and it starts to settle out of the water column. And because hydroxide has a positive, -1 affinity. Phosphate has a -3. The phosphate substitutes into this polymer, so essentially forming the aluminum phosphate. And that's what happens in the sediment. That's what happens when it strips it out of the water. So that's the chemistry. Whether you get a lot of geeky stuff, other folks, it just grabs the phosphorus and takes it out and holds up.
So do you find that adding the alum has an impact on the pH in the lake formation and the hydrolysis to H2SO4?
Absolutely.
Yeah.
So, anything that's in activation that I do anymore, always is both. Okay. If you're doing a low dose, just a maintenance dose, a stripping dose, you can do it in such a way that it probably don't affect the alkalinity. But when you get high enough to get that ratio of aluminum in sediments high enough, you're going to need to use, I use sodium aluminate because alum is a salt of an acid. You take alum ore, use sulfuric acid, produce that. Sodium aluminate is a salt of a base. You use sodium hydroxide, produce sodium aluminate. You combine those, they're stoichiometrically then combined. You're using aluminum, so you don't have to have another compound that's not of use. It's still grabbing phosphorus, but they balance each other out volumetrically 2 gallons of alum to 1 gallon of sodium. Aluminate, you won't change the pH. I've done this in 50 lakes, more than a tenth of the pH if you do it right. If you vary more than 5%, you can have a disaster. 17%, you can have pH go from 7.8 to 4.2 in 1 hour.
That will kill stuff.
Yes. That's why I started the conversation. You got to do it right. Everything you have to do right.
What's your liability coverage?
Still-
There is, actually.
So,
Actually, Terry wasn't involved. The applicator bore the liability because my spec said you do not vary the application from 2 to 1 volumetric instantaneous ratio more than 5%. So when they varied it to 17%, whoops. It was $1 million job. Contractor only got $650,000. But that was 7 years ago. Worst algal cyanobacteria blooming lake in the state, hasn't had a bloom since. Short-term fish killed, scrap fish. Fish and Game was happy because they got 3% fish. Everybody else was poor. Anyway. All right. Regardless of the metal, it's basically this thing. That metal is the active ingredient. It's a capture mechanism where you combine with phosphorus. You're transporting it either to the lake sediments or somewhere else. And what you're trying to do is add excess aluminum to combine with the excess phosphorus that's coming without the metal because of our land use versus geologic reactions. Okay? All we're doing is trying to get back to what we were before. Here's just an example of some lakes and some phosphorus reductions, longevity of the treatments. Longest reported effective treatment's been 20 years. Most treatments, depending on the state of the watershed, are going to give you somewhere between 8 and 12. Green Lake in the city of Seattle is an example of where the watershed is urban, north end of the city. Retrofitting that is going to take a long time, like the alum treatments lasting 8 to 12 years each. So it's an ongoing thing. It's just part of the solution. It's not cheap. I guess I just said that. Now, one of the concerns with a large lakes with a large wind fetch when you do the nutrient inactivation is that you're going to get that flock or that sediment redistributed into the water column. It's no longer reacting, so it's not going to affect the pH, but it's going to settle back down because its density characteristics are still there, so it just drops right back down. And the ratio is still there. But what will happen is eventually that recirculation will mix it with new sediment that's coming in, new organics, And so your effective depth will decrease and sink into the sediments, shortening its longevity. Like I said, Green Lake was last treated in 2004. It's probably going to have a treatment in 2016, 2018. Long Lake, Kitsap County, I'm meeting, County Council is called a meeting for March, where they're going to initiate a funding mechanism, a fee for those people living around the lake, to fund the next 10 years of the adaptive program, of which there'll be a treatment probably 2016, which gives Long Lake about 9 years before it has. Okay. There was an old slide that I used a while back. Anyway, this is an example of Grand Lake St. Mary's in Ohio, which is probably one of the worst lakes you'll ever be at. It's relatively large, but not anywhere near your scale. Lake, shallow lake, wind fetch. Watershed has totally trashed this system. I mean, the phosphorus that you're seeing in your lakes, 30 to 35 in there. We're talking about the phosphorus that easily gets up, and the inflowing waters is between 200 and 600 micrograms per acre. 60,000 people live in the watershed, equivalent of 5 million cattle, human equivalents of cattle live in the watershed, 3 million pigs, 12 million chickens. That all flows into the lake because all the water goes on the ground in the summer. I mean in the winter. So it's a big problem. Anyway, this was a demonstration of a large wind-fetched lake that is a water supply for those 60,000 people. That's their drinking water supply. It produces microsystems on average of 60 micrograms per liter. Okay? You have activated carbon. That was the first thing when I went to the lake. I said, do you have activated carbon in your water treatment plant? They said, oh yeah, we just installed it. But at 90% removal, you're at an average of 6 micrograms. It's above world health for water. Okay? So they needed to do something to keep the recreation going. We're several $1 million for recreation every year, but also for just treatment. They didn't have enough money to do it right, so we treated 2011, 2012, a total of 40% of the area, about 23% of the total dose. And this is one graph that shows the first 2 results. This is the model. This is all the data in the model going up predicting this. This is the actual reality after the treatment because we shut down internal cycling. That treatment was only treating 12% of the dose that was in. So it can have an effect. Okay. So totally, we haven't in the 2 years treated the whole system. It costs a lot of money, $8 million, to do about 40% of what's needed at the watershed. So initially, I've costed out there was going to be $20 to $30 million to do the inactivation to keep the system going. Watershed controls are $300 million. All ag, very hard to get done. So, let's just summarize that real quick, just give you an idea. Again, just a fraction of the lake's been treated, but the sediment shows that the phosphorus in the sediment has been inactivated in that 40% area, and the internal cycling within that was measured both with the sediment and the water column has decreased. Cyanobacteria blooms still exist, but at a lesser degree, but we're nowhere near there. It's a demonstration of what can be done, and they have to figure out where to go. Okay, I'm almost there. So this is just kind of a look at why in lake. When you're talking to folks, why do we have to do in lake? Here's just looking at some of the things. City of Seattle, mentioned that, Green Lake. Okay, BMPs, up to $1.4 billion to accomplish removal of that external. Whereas, you know, they spent $1.1 million big difference. Grand Lake mentioned 2 to 300 million versus 20 to 30 million. Okay, to get the same basic. So, my point being, you have to go after the watershed, but in order to maintain the beneficial uses of your lake, you have to look inside the lake too. So in summary, again, once the system has got to the point that its resiliency is burnt out, you have to manage the system in your lake, okay? If your lawn grows and it gets too tall, you have to mow it, okay? It's just the way it is. Sun and rain is coming down, it's gonna grow, okay? You have to always look at external controls. But you have to understand that shallow systems have multiple ways of making phosphorus available and growing deeper energy. It's not just stratified systems, the deeper anoxic zones that have internal cycling. The other thing when you're doing your mass balances, looking at things, look at the timing. When is the phosphorus becoming available? Is it after a rain event? Is it after a wind event? Or is it after a vertical transposing of the phosphorus to the algae themselves? All those things are. To date, and this is why I spent so much time on that one, it's the most effective inlay treatment across the board. Has it resulted in disasters? Yes, as has every other treatment. But we've learned from it. So if you do them right, you have a good system. That's it. Any questions? Good.
What is this?
It's obviously. I thought I was on.
It's obviously in a liquid form when you apply it.
You can apply it dry, yes, in small
You can apply it
systems,
dry.
but in larger systems, cost effective, it's got to be liquid.
Could you apply it on the ice and let it go into the water?
Good question. It's a chemical reaction that forms a hydrolysis first, that forms our aluminum hydroxide that we want to form, that phosphorus is then incorporated. That occurs 5 degrees or above. Okay, so it's best to do it at ice out, just after, because you add ice out to 4 degrees, just a little bit after you'll jump to about 6 and stay there for a while. That's the minimum temperature. And so they're all temperature dependent, any of the metals for aluminum.
A well-mixed system like Pigeon Lake is more efficient to inject it at depth.
Actually, an injection for Pigeon Lake where you can isolate some of the areas that are non-point coming in and influencing there, or some of the inflow streams, and have an injection system with a distribution, letting the wind distribute it to a certain extent, that may be much more effective than a whole lake treatment because of the condition where you're at. You're not that bad yet. You're bad, but you're not that bad yet. You're still at that point of recovery. You got to get after the watershed because it's obviously turning the corner. But you only need little tweaks. Now, your question, if you reach a threshold and you get it there, are you never going to have cyanobacteria? No. Cyanobacteria are going to pulse just like everything else pulses when the conditions are right. Is it going to be as intense or last for the same period? Probably not, because it's got more stressors now to reduce it. Yes.
You actually presented data that the cost benefit was that this in-lake treatment was actually more cost effective than doing BMPs. I'm not sure that we've actually done that analysis on Pigeon Lake yet. Does anyone in this room have data on whether watershed, like I always say, would we spend $1 million buying all the land in order to get back to forest?
There will be confusing information when you look at the
Yeah.
cost for removing phosphorus in different BMP treatments, like a passive wetland with some harvesting will be fairly cost efficient, okay? But when you look at the recovery, scale that as to the recovery of the nutrient balance driving the cyanobacteria blooms in the lake, that's what I was talking about. Okay, in order to stop the cyanobacteria blooms in Grand Lake St. Mary's, you need 300 million. Now, to be cost effective for the pound you remove, there are certain wet BMP trains that we've done in Grand Lake that are more cost effective per pound of phosphorus, but they ain't anywhere close to being treated. Yeah.
I know you're more interested in the science, but obviously, you know, it's proven to be quite effective. You can see quite a dramatic drop in phosphorus as well as your values. How do you keep the society around the lake at large from saying, well, all the problems are fixed, we don't have to do anything, you're going to go back and have the next green lawn?
Long Lake is an example. In Long Lake in 2005, helped the state senator write a grant. We went to the legislation, we got 100% grant for $1 million for 5 years. Part of it was education. Part of it was monitoring, in which I incorporated the citizens into that monitoring program. Part of it was managing aquatic plants. Terry was involved in doing that. Part of it was nutrient inactivation. That watershed awareness, the lake awareness, the public education has led, over that 5 years, has pushed a county that's totally very Tea Party-ish, totally anti-tax, into, they're now going to put it to vote to tax themselves to do it for another 10 years. And all the citizens around the lake, they went around and they got 88% of the citizens to sign a petition to go to the council saying, we'll vote for it. We'll tax ourselves. So it's education. It's working. Now,
I'd like to make a comment and a question on this issue of the cost of BMPs versus in-lake treatment. It depends on what you're doing and
how you measure it.
and how you're doing it.
That's right.
At Pine Lake, I don't think any individual project was more than 15,000, and it was all done by volunteers. So,
Right.
so
Yeah, it's all relevant.
if you're going to get into huge manure digesters and all kinds of stuff, then, yeah,
Exactly.
the sky's the limit.
Yeah.
And my question was, can you say anything about what the relative cost of microfloc injection with alum is versus whole lake treatment? I've always assumed it was cheaper, but
There, again, you get into life cycle costs.
yeah.
For instance, at Lake Oswego, we have injection going on there, and what we've done is a couple units of injection versus whole lake, whereas the other parts of the lake, we do whole lake every 15 years. So it really depends, again, it's by where you're doing it. The point being, if you're going to do an alum injection to intercept and then in time inactivate the sediments, so intercept the phosphorus, neutralize it before it comes in, then use the excess aluminum to inactivate sediments over a period of time, the amount of aluminum you have to add to the sediments is going to be more than periodic treatments because you're intercepting first and your efficiency is less, but because you're spreading it out over time, you may have less cost. It depends on the system and the size. The smaller systems are going to be injection is going to look for the short term, both capital costs and O&M costs over 10 years life cycle, less expensive. But it just depends on the system. What works. To me, it doesn't matter. It's locking up the phosphorus. The big thing we have to do, as humans, is recognize it's time for us to quit thinking that manure is natural, flushing nitrile is natural, and harvest both those resources for phosphorus. We're running out of phosphorus. We need to recycle. Okay, that's my point.
That's great.
Perfect, thank you, Harry. We'll break for 10 minutes here for coffee, and then we'll get started again at 1:45.